All right, guys, welcome back. So today we're taking a look at 4.5, solving our exponential equations. So an exponential equation, the idea of solving it, you want to isolate the exponential portion of the problem, where sometimes with certain easier ones, you'll be able to rewrite both sides of the equation with a common base. If that's impossible, you're going to take the natural log of both sides, applying power rules and other rules for simplifying logs, and then solving the equation out from there. You'll find if you can rewrite them as a common base, you'll generally be able to give me an exact value, either as an integer or a reduced fraction, whereas if you're going to rewrite it with logarithms, then you're going to have to use the calculator. So if we take a look at this simple, straightforward one right here, we can see we can rewrite the 16 as a common base, because 16 is just simply 2 to the 4th power. So we have 2 to the 3x equals 2 to the 4th to the 1 minus x. So power to power means we multiply, and that becomes 2 to the 4 minus 4x. Now once the bases are the same, the exponents are equal. So 3x equals 4 minus 4x, and then we just solve that linear equation, and we get 4/7 final answer. So we're not worrying about rounding to the thousandths place. We're going to leave it in the fraction form because it's an exact value. There's no need to get it as a decimal. But the key is common base. Either one side can rewrite as the common base, or sometimes both sides. The 27 and the 9 can both be 3 to a power. 3 cubed for the 27, and then 3 squared for the 9. So then that becomes a 3 to the 12x minus 9, a 3 to the 4x plus 2, where once again, common bases, exponents are now equal. 12x minus 9 equals 4x plus 2. We get 8x equals 11, therefore x is 11/8. Again, we'll leave it as the exact fraction rather than trying to approximate it as a decimal. So for any question of this kind of style where you can clearly see common bases, this is exactly how you want to solve this. You could do the natural log method that we are going to explore in the next couple of examples, but it would be completely unnecessary and not exactly in your best interest when you can just do a common base instead. Now here you'll recognize we have to do a natural log because we don't have a 129 becoming 2 to a power. 2 to the power of 7 is 128, so our answer is going to be pretty close to that, but it's not going to be exact. So the general idea is we take the natural log of both sides. Because as we explored with our log properties a couple videos ago, the exponent becomes a coefficient, so this becomes x ln of 2 equals ln of 129. And then we can go ahead and divide over our ln of 2 from both sides, and we can use our calculator. Ln of 129, make sure you close off your parentheses. Divide by ln of 2, close off your parentheses. We're going to get 7.011. So just make sure you're careful with how you're typing that kind of stuff out into the calculator there with the ln, 2 natural logs dividing. All right, so that's a little more straightforward example with a natural log situation. Here's one that's a little more complicated. So we've got 9 times 3 to the x equals 7 to the 2x plus 1. So before we worry about natural logs of both sides, we've got to make the left side a single exponential problem. And for this thing right here, we can clearly see 9 and 3 can combine, because 9 is 3 squared. And then when we multiply like bases, we're adding exponents. That becomes 3 to the x plus 2. So now we can take the natural log of both sides. Ln of 3 to the x plus 2 equals ln of 7 to the 2x plus 1. The exponents become a coefficient, which means that we have a binomial expression multiplying with our natural logs here. So if I want to begin the process of solving for x, I'm going to have to distribute first. So we're going to get x ln of 3 plus 2 ln of 3 equals 2x ln of 7 plus ln of 7. So to solve from here, we need to get the x's all on the same side. So I'm going to go ahead and I'm going to subtract over the 2x ln of 7 to the left, and then I'm going to subtract over the 2 ln of 3 over to the right. And then while I can't combine x ln of 3 and then the negative 2x ln of 7, I can factor a single x out and get ln of 3 minus 2 ln of 7 there in parentheses. And even if we could factor out more, let's say they both had a number in common. Let's say instead of being just x ln of 3, it was like 4x ln of 3. I would still not factor anything that they had out in common besides just the x. Because the whole goal is to solve for x. So if I factor out a 2x, I'd still need to divide the 2 away as well. And that's now when we divide over this expression, ln of 3 minus 2 ln of 7 onto both sides. Now, getting this answer, which should be 0.08997. So 1,000th place, technically that's 1,000th place 9 would round up to a 0, making the 8 a 9. So it would really be 0.09. If I just showed more digits there, just kind of give you the right idea. This process, that can be a little confusing. You want to refer, so you pretty much want to pause this video right here and then go over to the calculator playlist that I have and find the one involved with logarithms. It will talk about how to type something like this into your calculator, show you step by step with both the older 83s, how that would work, and then with the newer 84s, certain advantages it has to type this into one step so you have an exact answer. It's all about just being careful with your parentheses, careful with your fraction options to create this results. But pause here, go watch that and come back to this and verify you're getting this particular answer. All right, so we have this equation right here, which you'll recognize this when we get into more of the word problems format. This is kind of like a compound, not necessarily compound interest, but this is a decay question kind of setup. So the idea is we're going to divide over the 1800 first. Now, when we divide over this number, it may not go into it nicely. It does in this particular case. It gives us a nice fraction, 1/2. It's not necessary to actually reduce it. You could leave it in that fraction form and solve this out perfectly fine. Now, from here, when we take the natural log of both sides, the natural log is going to cancel the e, leaving just that exponent, negative 0.000179x, and then ln of 1/2. And then we divide over the negative 0.000179 with that ln of 1/2, making sure that when we put it into our calculator, the ln of the 1/2 is closed off in parentheses before we're dividing by that negative number. And we should be getting 3,872.331. All right, so just be very careful. Again, refer yourself to the logarithm calculator video to kind of show how the logarithms are working inside our calculator options. All right, now 2 remaining special types of exponential equations are equations that you'll notice we can get a common base for the 9 and the 3, but there's that plus number on the other end there that we can't get a common base with. While 3 does divide into 6, it's not a power of 3. This is a disguised quadratic trinomial, where we can recognize if I move it all over equal to 0, the 9 is really 3 to the 2x power. 3 to the x minus 6 equals 0. Now, if we use a dummy variable like w to replace 3 to the x, this is w squared minus w minus 6 equals 0, which we know how to factor quadratics. We can do that pretty quick. This is w minus 3 and w plus 2, so w equals 3 and negative 2, which obviously was not the original variable, so we got to set that back equal to 3 to the x. So if w is 3, 3 equals 3 to the x, that means x is just simply 1. That one's nice. On the other side, exponentials can never equal negative, so nothing there is valid. Even if you tried solving it out using your natural logs, you would have a natural log of negative 2 equal to natural log of 3 to the x. Natural log of negative 2 equals x ln of 3, dividing over the ln of 3. You're not going to get a real answer for that. You'll get an imaginary answer. We'll talk about natural logs of negatives in Unit 11, I believe 11.6. But it gives you an imaginary answer, so it's not really relevant anyway. So even if you try to solve it out, it would still give you no dice. So just right off from the beginning, if you have a negative equal to an exponential, can't use it. It's done. Now, obviously, our answer for w, the positive 3, worked very well for the 3 to the x, but if it didn't, then we would just do natural logs of that one and kind of solve it out. So again, you're recognizing that you have 2 exponential terms. One is the square of the other, so this is the w squared term. This would just be the w term then, that's 6 to the x. And obviously the 4 is the coefficient of w. In this case, it's 4 times 6 to the x. So our w represents 6 to the power of x. So again, it's a quadratic trinomial. So we go ahead and move over the 4w and the 32. You get minus 8 and plus 4. So we get positive 8 and negative 4. So right off the bat, the negative is out, because a negative cannot equal the exponential, but we can solve the positive 8 equals 6 to the x. Natural log of both sides. Rewrite that as x ln of 6, so divide over the ln of 6. and making sure in our calculator we're closing off the individual parentheses around the 8 and the 6, and you will get x to equal 1.161. All right, so that's our exponential equations. Make sure, again, you're referring to the video on the log uses if you're unsure of how to type out certain portions of this into your graphing calculator. All right, so next up we'll be solving log equations, so I'll see you guys next time for that.